So this is the Rho method, which is really quite interesting. And it goes like this. If you're trying to find hash collisions, now if you have a hash function like MD5, right, that means, let me bring up a command prompt here. All right, so all right, clear. All right, so I think I can do MD5 OpenSSL MD5. Yep, and I think I can echo like hi to OpenSSL MD5. Oh, MD5 some perhaps. I may have to fine. Just a whole one. MD5 some exists, and let's find out how you feed in the data. I can use an online one if this is annoying. All right. Oh, there might be MD5 on the Mac. There it is. Okay, MD5 minus S. Hello. There. That's the point of a hash. It gives you these semi-random numbers, and if you change anything about the input, then it has, like you change the O to a P, then everything changes. This is a proper hash function. It always has the same length no matter how long the input is, and every single bit change in the input changes like half the bits in the output randomly, so there's no pattern at all. But it's not random, it's repeatable. If you hash the same thing again, you'll get the same answer. So the point is, if you are downloading a file from a server, you can record the MD5 hash, and then you download it, and then you check to make sure the hash is still the same, and then you know you got an exact copy of the original file. But I could put in really long strings, longer than this, and the hash would not get any longer. And therefore, there are more total strings you can use for input than there are hash values. So in principle, there are two strings that will hash to the same value. In principle, there's an infinite number of strings that would hash to the same value, and those are called hash collisions. And you don't want there to be any hash collisions, because then the fundamental property is not true. You download a file, it's supposed to have this hash, you calculate the hash, but if there's two files with the same hash, then I don't really know that I got the right file. It could have been modified, but still had the same hash. So what you want, it's impossible for there to be a hash function that does not have any collisions. Just from a fundamental logical point of view, the fact that it has a fixed length means there will be collisions for long files. But you can make it so long that those collisions are so hard to find that you will never find any, and there are none of them in practice. And so now the question is, what is an algorithm to find hash collisions? And when I first did it, I thought you would just input strings like 1, 2, 3, 4, 5, AA, AB, AC, AD, just have an increasing list of strings and hash them all and look for collisions. And you can do it that way, but it's not the most efficient way to do it, because you'd have to have a huge memory to remember all those hash values and keep looking through this huge list every time. So this is the insight called the Rho method. If you hash a starter string, and then instead of moving to the next string, you hash the hash, and then you hash the hash and hash the hash, this has the property that as you go along, eventually there will be a collision where one of these creates one you have seen before, and when that happens, you will just stay in this loop forever. So now you could do something like only keep every 10th hash and check if it matches, and somewhere on this loop it will match. So you could save a lot of storage at very few extra cycles. And it turns out that in general, if you take the total number of hashes and take the square root of that, the length of this tail is approximately the square root of n, where n is the total number of hashes, and the circumference of this circle is approximately the square root of n. So that gives you a clue how long it will take. So this is a good cycle, and so you can do things. Now in Python, it's extremely easy to calculate hashes. So let's do that. If I do Python 3, and then import hashlib, you can just do this, and that will do an MD5 hash. So this is a new MD5 object. It's going to encode this A A is the password, it encodes it with ASCII, and then it gives me the hex digest of the hash. So that's the story. And so now we are going to truncate it by just adding this -2 colon, so it gets only the last 2 hexadecimal bytes of it, because I want to make a really short hash for demonstration purposes. So now I have a hash that's only 2 characters long. So obviously there aren't very many of these at all, and I won't have to hunt too far to find a collision. So now I can make an iterated function here. And if I paste that, this is going to start with A, and now it's going to calculate 50 hashes where H is the hash, and it's hashing H. So it starts with H equal to A and hashes it. Next time it uses the old H to hash and the old H to hash, so it hashes the hash over and over. And it does 50 of them, and there they are. And you can notice that there's, say, a 21 here, and there's another 21, and there's another 21. So we have hit the loop. And if you want to find the loop, one easy thing to do is just change the width. No, it's not going to wrap. Okay, let me run it again. There we go. And I'm going to put it in a text editor, which will wrap. All right. So here's the output, and I can just drag this in there until I see them line up 59, 59, C3. So the loop starts here. There's the loop, there's the second cycle. So that's the story. And you can see this is the row, this is the tail, and this is the loop that just goes around and around and around. So that's how you find these things. And so there's various challenges to find here with medium and longer hashes. And there's another project later where we do some of the more cool mathematical stuff you can do with the Rho method. But that's a useful thing to know about the property of hashes. Now, I'm going to stop this one.